A warm welcome to Dr. Zainul. So we are from Group E, would like to present our design and simulation of circular slot microstrip patch antenna for 5.5 gigahertz application. Before we jump into the presentation, I introduce myself and also my teammates. Me, myself, Sachin Prakash, and my team consists of another two members, which is Sanjeev Kanakan and also Privan Rameshwaran. So let's move to design specification. Our main objective are design a circular microstrip patch antenna operating at 5.5 gigahertz. Second one is improve gain and return loss using a circular slot structure. And third one is evaluate antenna performance through CST microwave studio simulation. And this is the circular slot structure. So for antenna specification, the type of antenna we used is circular microstrip patch antenna, which is operating at 5.5 gigahertz frequency, which has substrates FR4 epoxy, which is 4.4, and feeding method we used is microstrip line feed. Next, we move to design requirement. Target resonant frequency for our design is 5.5 gigahertz. Return loss, we are expecting less than negative 10 dB, VSWR less than 2, and radiation efficiency more than 60%, target gain more than 6 dBi. Let's move to antenna design calculation. So as we know, our frequency is 5.5 gigahertz and our epoxy substrate is equals to 4.4 and our H is equals to 1.4 millimeter. After we imply the values in the formula, we got F equals to 7.619 millimeter, and same goes to the actual radius. Once we include the values in the formula, we got A equals to 7.25 millimeter. And next, for the baseline substrate dimension, there are two calculations, which is the first one is L sub, we got 29 millimeter, and W sub is equals to 29 millimeter. So W sub for 1 times 2 array is equals to 58 millimeter. A circular patch antenna inherently occupies 16% less physical space than a regular patch antenna at the same operating frequency. This satisfies the compact size constraints required for wireless wireline application. A conventional rectangular patch requires adjusting both length and width simultaneously. In contrast, a circular patch has only 1 degree of freedom to control its radius, making it simple to design and optimize. Okay, let's move to antenna design and material. For the top layer, we choose copper, which is thickness of 0.035 millimeter. For middle layer, we choose FR4, which is thickness of 1.4 millimeter with relative permittivity of 4.4. For bottom layer, we choose copper with thickness of 0.035 millimeter and structure of dual square defeated ground structure windows. Before we go into design process, I would like to explain about the design front view and back view. So this is the front view and this is the back view. The front view got two circular, which is our first proposed method is circular patch. So this is the circular patch. And second method is 1 times 2 array. So this both combined to become 1 times 2 array. So in one design, we have explained two method using a single design. So this is the front view, this is the back view. Okay, let's move to design process. Select target operating frequency 5.5 gigahertz for C-band wireless application. Next, calculate initial dimensions for the circular patch elements and the 50 ohms to 100 ohms corporate power divider fit network lines. Next, choose substrate material and move on to model the 1 times 2 circular slotted patch array layout in CST Studio Suite, and then introduce a defected ground structure with dual 20 millimeter square cutouts on the background plane to enhance the performance matrices. And last but not least, simulate and fine-tune structural parameters iteratively to optimize S11 return loss and maximize realized broadside gain. So this is our design parameters. Let's move to S parameter result. For our design, our return loss for S11 is negative 11.99 dB at 5.5 gigahertz, which is located at here. It passes the industry standard, which must be below to negative 10 dB. So this proves that the antenna we designed absorbs over 90% of the signal power instead of bouncing it back and wasting it. Let's move to the 3D radiated pattern result. So this picture shows the radiated pattern for our design. So the peak gain of 6.19 dB indicates a high directional signal strength. Radiation efficiency of 83% confirms low energy loss as heat inside the substrate, which is this calculation. Next, the total efficiency of 78% successfully passes the standard 60% benchmark for real application performance, which is the total efficiency. And finally, the radiation pattern displays a clean broadside shape that directs maximum energy straight forward. Let's move to the conclusion part. The 1 times 2 circular slot microstrip patch antenna operating at 5.5 GHz was successfully simulated and verified using CST Microwave Studio. The design achieves excellent impedance matching at 5.5 GHz with a return loss of negative 11.99 dB, surpassing the standard negative 10 dB industrial benchmark. A peak realized gain of 6.19 dB and a clean broadside radiation pattern are obtained through the 1 times 2 array configuration and the corporation power divider feed network. The radiation efficiency of 83% and total efficiency of 78% comfortably exceeded the baseline minimum project target of 60%. Performance metrics are successfully enhanced using optimized patch slotting rout equals to 5.3 millimeter and R inner equals to 3.1 millimeter alongside dual square defected ground structure windows on the background plane. The circular patch choice provides a 16% physical space reduction compared to conventional rectangular patches to satisfy compact WLAN application constraints. Last but not least, tuning and optimization are simplified because the circular geometry offers a single degree of freedom via its radius instead of requiring simultaneous length and width adjustment. That's all from us. Thank you, Doctor.